Shanghai GDG is a very interesting developer community.
I'm glad somebody has asked this question.
This is where the magic happens.
This is primarily a question and answer show. So if any of you out there would like to ask questions.
Hi everyone, my name is Ryan Boyd and I'm a developer advocate at Google on our cloud data services such as Google BigQuery.
And hi, I'm Michael Manicherry. I'm a developer programs engineer working with the BigQuery product.
And today we're here to talk about best practices for querying massive data sets. This is a video that's particular to the querying aspect of BigQuery. We have other videos that talk about BigQuery as an overview and how the API works and how to get your data into BigQuery. But today we're going to really concentrate on querying BigQuery. If you have any questions after watching this video, feel free to reach out to us on Stack Overflow. There's a Google-BigQuery tag there on Stack Overflow, and ask your questions, and we'll be happy to jump in and answer them. We also have our Google Plus profiles as well as our Twitter handles on this slide if you have any follow-up questions that you want to ask to us individually, maybe to clarify what one of us said during the episode here today. All right, before diving into some example queries with BigQuery, I want to actually show you the way that BigQuery works, the way that BigQuery processes its queries. So let's jump over to this slide here. And this is basically the BigQuery processing tree. This is how BigQuery queries are processed. And I'm going to talk a little bit about how this is different between BigQuery and a typical relational database. So a typical relational database, you load your data in, and the relational database makes an index of that data. And then anytime that you're performing simple queries that are easy to select from that index, a relational database is fairly quick. But if you're trying to do really, aggregate queries over those large data sets, the indexes oftentimes won't find a match. The aggregates aren't stored in the index, especially if they're more complicated aggregates or over a sub-selection of the data. So it needs to do a full table scan. And a relational database doing a full table scan is sort of like the heart attack for the DBA. DBAs hate the idea of full table scans because they're really, really slow when doing it on a relational database that's typically hosted on a single server. There's only so much I/O bandwidth for that server, and so you have really bad performance. And BigQuery is actually the absolute opposite of this. We embrace the concept of full table scans and allow you to query over terabytes of data in just seconds. So we're going to show you some of those big queries here soon. But first, I want to really give you an understanding of what happens underneath the covers when BigQuery processes its queries. For those geeks out there, if you don't care to know about some of this stuff, you don't have to. That's the awesomeness of BigQuery being a web API service. It's really easy to use without knowing this. But knowing some of this, helps your geek inner heart, but also makes it a little bit easier to understand, how you can optimize your queries. So this is the tree structure, again, very similar to like a relational database. And in this tree structure, we basically have the storage at the bottom, and each leaf node in this tree is basically assigned to deal with a very small subset of your data from that distributed storage. So think about something in the order of tens of megabytes of data that each leaf node is reading off of that distributed storage. Now, the distributed storage is distributed, as its name implies, so it basically has a lot of different disks, a lot of I/O bandwidth. So each leaf node can simultaneously, in parallel, read off this distributed storage really quickly. And they're loading in the data from that they're tasked with dealing with. So think about, the leaf on the left is dealing with essentially rows 1 through 10, and then the next leaf over is dealing rows 11 through 20 or something like that. So each can independently process its own chunk of data and do sort of the aggregate queries on its own chunk of data. So you think about something like a count query. So the first leaf would count the relevant rows, the second leaf would count its relevant rows, and then it does this partial reduction as it moves up the tree, where the mixer above it would add those two counts, would sum those two counts together, and that keeps on going up the tree until you get the final result. Now, one thing that I really should emphasize here, are actually two things, is one, our reading from the disk with BigQuery is only reading the columns that you're accessing. This reduces the cost to us to run the queries and thus reduces the cost to you. And this is all because of the columnar data storage. So we only need to read the set of data that's in the columns that we're touching. The second thing I should note is that this is really different from like a MapReduce-based system, which people often try, frustratingly, to compare to BigQuery. And the way that it's different, one of the big ways that it's different is that we are only reading from disk at the very beginning of this processing tree. We're not actually reading and writing from disk constantly throughout this operation, which is what a typical MapReduce operation will do. MapReduce, in between the map, shuffle, and reduce steps, will often write and read a lot of data from disk, and disks are the slowest point in this whole tree. And also with a typical MapReduce operation, you're going to be performing multiple map steps, multiple reduce steps, and that just gets really heavy on those disks. Whereas with BigQuery, it's able to take advantage of the super fast network bandwidth that BigQuery has to offer. All right, so that's kind of covering the true geek side of BigQuery. But now let's show this in action. Let's show what happens when you run a query and see some queries over very large data sets. So the first table that I'm going to query over here is basically all of the page view data from Wikipedia for a particular month. So what each of the rows in this table represents is an hour-by-hour look at all of the Wikipedia page views that happen in that hour, grouped by the title. So in this case here, we actually have the Wikimedia project. So this actually includes stuff other than Wikipedia, but all the Wikimedia project, and the language of the page, and then the title of the page, and how many views it had, as well as some bytes transferred data. And as Michael would say, there's a long tail here. There's an extreme long tail. There's a lot of pages that are just viewed once an hour or things like that.
But altogether, this table size is it's a terabyte of data per month, and we're looking at something like 650 million rows for an entire month.
Actually, I think that row count is off here a second. We have a bug in our UI. This is actually 13 billion rows.
Oh, 13 billion, so my mistake.
And we can actually show you here. I'll do a very quick count star query. Mm-hmm. And we can see here, so these are the page views in Wikipedia for July 2010. And yeah, it's 13.5 billion rows that are in this table.
Yes, for a single month.
For a single month, and it's over a terabyte of data. So let's show the type of query that we're going to run on this. And the query that we have for you to run on this is actually kind of an interesting query. And it's really showing the power of BigQuery. And so I'm showing it a couple different ways. First of all here, the simple aggregates. Michael's going to be talking about some of the other aggregates here shortly, but the simple aggregate of a sum is a very common operation, especially with log files and things like that. And then we're basically getting the top viewed titles, top viewed pages, essentially, from Wikipedia, and we're getting the 100 top viewed pages. But we're restricting the set down a little bit, and we're restricting the set with this regular expression. Now think about, on a relational database, trying to perform a regular expression on 13.5 billion rows. If you guys want to try that out there and give me how long your relational database takes on doing a regular expression on 13 billion rows when it's unindexed, these are ad hoc regular expressions. I can change this however I want. Try running that and give us a shout out on Google Plus and let us know how long that took.
Imagine building the horror of building an index on something you don't know yet, the regular expression itself.
Yeah, exactly. You could probably, in some relational databases, build an index on a regular expression, but you wouldn't be able to change the regular expression then. So it would take a long time to build up that index each time if you wanted to do different types of analyses. And that's what BigQuery is really good at, is kind of this ad hoc iterative analysis. So in here, we're basically doing a regular expression on those 13.5 billion rows and finding all the pages that start with a capital G, end with a lowercase e, and have two O's in between. So think about a page that looks something like Google. And we're finding the top 100 of those pages. So this is kind of our inner query. We also actually do something in our outer query to do more regular expression magic, and that is kind of formatting the titles of these pages. So if you notice when you visit Wikipedia, the actual URL has underscores in place of all the spaces in the URL. We want to strip those out to make this very easy for us to view. So we're showing how we're doing a subselect in this query as well. So I'm going to hit Run Query. And I will note that this query, takes a little bit longer than the typical query in BigQuery because it is going over such a massive data set. Typically if you're querying hundreds of millions to a few billion rows, you're getting responses in like 7 to 10 seconds here. But in this case, we're actually querying over this 13.5 billion rows and over a terabyte of data. So it finished in 22.9 seconds. And actually, I got rid of that here, but at 22.9 seconds, it's 505 gigabytes of data that it processed. And the reason that's different than the 1 terabyte of data number that we saw earlier is we're actually only accessing particular columns. Remember, we mentioned about the columnar data store of BigQuery. We're only accessing the title, the views, the Wikipedia project, the language. We're only accessing a subset of the columns in this table. So we're only hitting about half of the data. So 505 gigabytes, I think it was 23.9 seconds or something like that. And we can see here all the page views of the pages that matched that regular expression.
This is an amazing query with a lot of value. You can see that it's looking at products, and you can see which products have been more viewed on Wikipedia. There's some information about health. There's some disease here. So you can actually look and see what people are actually searching for in a matter of seconds, really.
So we often use this Wikipedia data set to kind of show off some of the power of BigQuery because it's a great open data set, freely available to access. We actually downloaded all of this data off of dumps.wikimedia.org. But you can see the analogy here probably between this and some of your business problems that you may have. So you think about sort of views on advertising, and the click-throughs on your ads. That can really add up as you have your ads on, hundreds of millions of mobile devices and web browsers. That can really add up. And this same type of query is often used for things like that. So for instance, if the title of the Wikipedia page here was the ad campaign, and you could figure out which ad campaign got the most views when that ad campaign was a particular type. And maybe that type could be a simple regular expression or something like that. So these queries are really, we're doing them in Wikipedia, but you can think about your own business challenges and what types of queries you'd want to be able to do. But a terabyte of data in 23.9 seconds, it's not really a bad query time here, especially with being able to do regular expressions on all the rows.
So in this query, we had a simple sum aggregate. So let's take a look at some other aggregate queries that are possible to do with Google BigQuery. So when I talk about aggregates, I'm not just talking about sums. I'm talking about things like counts and basic statistical measures like standard deviation, average, variance, and things like that. Like Ryan said, in a relational database, sometimes we try to solve the speed problem with querying for aggregates with indexes. Of course, that's challenging in itself. With a document store, something like CouchDB, you can run aggregate queries, but oftentimes you have to write your own custom MapReduce. What's great about BigQuery is it combines sort of the best of both worlds. You can express these aggregate queries in terms of a SQL-style language. So let's take a look at some of these examples. This is a really interesting query. We're going to look at birth weights by state. So we'll just pick Ohio in this case, by a particular year. And we're going to look at how cigarette use of the mother affects the birth weight.
And this is actually a public data set that you can play around with. All of our public data sets, many things that we're talking about here are available in the public data sets on BigQuery. You can look in the table of contents. I think it says public data sets or sample data sets, I believe. And all of these are available. Play around with them, and let us know what interesting queries that you come up with. But let's show this example here. And if there's any of the things that we're talking about that aren't there yet, we will work on coming up with some other data as well.
This is a good opportunity to tell you that you have a query quota that's free. So you can actually try this out for free and do some queries and learn how to use it without billing turned on. So let's check out this query. Let's see if there is a difference between mothers who smoke and baby weight for this particular year. So wow, that was a very fast query. In just 3 seconds, we returned this data. Looks like we processed about almost 3.5 gigabytes, just 3 seconds. And you can see when cigarette use is true, it looks like the baby weight is slightly smaller. It's actually quite
a half a pound difference.
Yeah.
We should warn, we're not statisticians here. We're not defining causation, but just correlation. But a half a pound difference when the mother said that they smoked cigarettes. Now, not sure that those answers are always accurate to that question, but a half a pound difference, and we can actually see here the mother age is different too. So it looks like the mothers who are giving birth to children who smoked cigarettes are actually about 2 years younger than the mothers who said that they didn't smoke cigarettes. And I don't know if that has anything to do with cigarette use in general, or if that just has to do with the ones that would admit to smoking cigarettes. But it's still an interesting type of ad hoc analysis that you could do here, and especially with the group bys, averages, standard deviations.
You mentioned piping this data into a statistics package to do a little bit more analysis on that as well. It's very simple.
And actually, we don't have this prepared here today, but since you brought up statistics packages, oftentimes people will take data out of BigQuery and do like a hash function on it. And they can do that hash function on it to select sort of a random sampling of their data then to use in a statistics package. Most statistics packages won't support, if you have hundreds of millions or billions of rows of data, but you can use that BigQuery hash function to select your random subset. Use hash and then mod that by a particular number. So
let's look at another example. This is an example actually that Ryan came up with. It's an interesting use of BigQuery to bucket births by sex and by state. So what's great about this is it uses a conditional statement. So if you can see the statement, we're selecting by state, and we're saying if is male, which is a Boolean, label that as a male birth, otherwise female. We're going to do a count per and group by state. The other interesting thing is we're using a function called having, and having is a lot like a where statement, but we're using the aggregate data, in this case the count, to compare. So that was a very fast query. As you can see, like some of the more populous states like California, you can see how many births were male, how many were female, and we're counting only states with over, is it 5 million births?
Yeah, over 5 million births. Well, only states that have 5 million births of children of the same sex.
Right.
So it looks like Texas had more than 5 million births of males, but less births of females. But Texas and California apparently are quite populous.
This is really interesting. So let's take a look at another statistics query. We're going to look at a standard deviation query. So let's take a look at, I was really interested to see if there were any outliers, and standard deviation is a great way to look for outliers. So what we want to do is figure out what birth weights are several times a standard deviation higher than average, and sort of get a baseline.
So just trying to find that query here quickly. Let's see here.
So
there we go.
This query is looking at the entire natality data set. This is a full table scan, and we're finding the average plus 4 times the standard deviation away. And here we go. In just a few seconds, we found that it's about 12.7 pounds. So that's several standard deviations away from the average. Now we can take that value and run a similar query and find if there are any outlying months and states where babies were a little bit heftier than that.
And Michael's going to have to point out this query for me here again. Where we go here.
So here we're going to take that value that we got in the standard deviation query and rerun it on the entire data set and look for outliers. Oh, look. So it looks like Maryland in 1990 in December had 12 babies that were very far above that, 4 times the standard deviation away from the average. So I'm not sure exactly what's going on there, but it's interesting that that's a slightly smaller state than some of these other ones like New York and California. So it looks like an outlier case to me. So you can use BigQuery to slam through tons of data to find cases like this with these statistical queries. And I just wanted to highlight another query. It's the quantiles. So quantiles are a way to find to bucket records based on a certain variable, meaning we can split up records into a certain amount of buckets with roughly the same amount of records in each. So in this case, I'm going to use the quantile query to look for split up into 10 buckets based on weight in pounds. And so these are the boundaries. In just a few seconds, I found the boundaries where there's a certain amount of babies in each. And this is another great way to look for outliers as well. Actually, you can look at the edges of the quantiles and see, what are the ranges there. And it's just a great way to go through a lot of data and find outlying statistics.
So I think now we're going to jump outside of the birth statistics data and take a look at another type of data that developers may use BigQuery with, and that is sort of log type data. And so we're going to look at the Wikipedia data set again, and the revision data set in particular. And I think that there are a couple different things that we need to look at when it comes to logs, log data. So think of the web application logs or what have you that we talked about earlier. And the two things or three things that we're going to look at here are information on a domain. And so let's start off with that. And then we'll also talk about dealing with dates and times in your logs, as well as dealing with IP addresses in your logs if you have any of that information.
One of the original use cases of the technology that BigQuery is built on was to actually analyze petabytes of log data that Google was producing. And this is a great use case for BigQuery and a very common one as well.
Yeah, so if you think about logs on our side, if you think about things like click-throughs on ads and things like that, there's interesting log data to analyze here. But we don't have all this information in our internal logs, but Wikipedia makes some of this information available, and it's rather interesting.
So this is an interesting query. We have information about the GitHub repository commits. So one of our fellow DevRel engineers, Ilya Grigorik, had compiled all of the GitHub revisions after a certain amount of time and put it into a data set here. So now we can look at the repository homepage information, and we're using a function called domain, which actually just pulls out the domain name of the homepage. So we can actually quickly look through all of the commit messages in GitHub and show where people are calling, what they're calling their homepage. And you can see like Khan Academy is there, SourceForge and Mozilla. And this is great for if you have logs, you can quickly see where your referrers are coming from with this function.
And so if you actually want to learn a little bit more about the GitHub dataset, Ilya is giving a talk upcoming at the Strata New York conference, all about how he used BigQuery to analyze his data, or the data in GitHub and all the repository commits and some of the information that he discovered from that. So I think Strata is still open for registration if you want to go see that talk in person, although they'll probably put some of that online as well.
So let's look at some of the IP functions as well. We have functions in BigQuery that allow you to convert IP addresses from a human-readable format to either a binary or unsigned integer format for various applications. So here's an example. We're going to look at the IP addresses tagged to the Wikipedia revisions, and sometimes they are recorded. And so here we're just parsing the IP and we're returning the result as an unsigned integer. We also have functions to return the result in a binary format, and you can use that for storage or for comparison, or for other applications that use that format. And you can also convert back to the human readable format as well.
Yeah, it's less interesting to show the binary format in our web browser here, but so yeah, we showed that with Wikipedia. Now let's also talk about the dates and times. And before we show you the queries on dates and times, let's just talk quickly about how dates and times are often stored in BigQuery. And BigQuery does not have a native data format for dates and times. BigQuery, typically you store your dates and times in time since epoch, so time since January 1st, 1970. And you store it that way because it's really simple to sort that information within BigQuery as integers and do sort of comparison and range queries. But sometimes it's not always easy to view your dates and times when they're in that format. And you're trying to get something human readable. We'll show you an example of how you might get a human readable revision time here from Wikipedia.
So we're using the format timestamp function here, and we're going to just take that timestamp and it's going to return the result in something that you're more used to, something human readable. It looks a lot like what you would see in a SQL style database.
Yeah, and here we're kind of bucketing into the actual timestamp. So it looks like there's some automated processes that may be making a lot of queries in any given second, or sorry, a lot of revisions in any given second on the Wikipedia data set. But often what you might actually do here is actually bucket into days or months or things like that. And there are other timestamp functions in BigQuery for you to check out that allow you to bucket it that way. And of course, you can use things like the regular expression, syntax and functions in combination with the time function. So, for instance, if you wanted to, match just those in a particular month or group by a particular month, you can use the regex extract functionality. Or the much easier way, if you had something like this and you wanted to just group by the month, year and month, would just be to use left. Very simple. Take the leftmost.
It's one of the many string functions that we have, right? So that is a good way to do it.
All right, so that's dates and times for you, and we talked about IP addresses and domain names and other types of interesting information that you might want to have if you have, logging web application events or marketing data or things like that. Now let's jump into one other thing with the Wikipedia data set, which is doing things like top. So if you wanted to, for instance, find the top Wikipedia articles that are most revised in Wikipedia, you might do a query like this. We're saying the top 10 titles. You always have to do count star when you're running this query from these 350 million rows in this data set. And we find out that the top 10 top 10 pages that are most modified are often these kind of special pages in Wikipedia. They have colons in them. So the page about vandalism is most modified. I don't know if that's people actually working on combating vandalism or people vandalizing the page about vandalism.
So what's interesting, so top is a shortcut for group by, order by, and limit. And what's interesting about top is that it uses a statistical approximation on these large data sets. So it actually can return a result quite quickly. So here Ryan is modifying this to take out titles with this colon in it.
And I reverse this a little bit, and I'm supposed to say, and not title contains, because contains returns a Boolean value here.
You can iterate quickly with BigQuery.
Exactly, even when you're making mistakes.
So we've taken out some of those special pages and administrative pages. Now we see regular Wikipedia titles that you're used to, such as George W. Bush and list of wrestling employees.
All right, so there's one other topic that we wanted to talk here about today, and it's something that we've been working with lately on some demos and all we've been trying to build. And we're working with our colleague Josh over in the Geo group in developer relations at Google, and he's been helping us out a little bit trying to query geospatial data. So there are a couple different ways to query geospatial data, but first we need a data set to query. There is a public data set out there available that has collections from a bunch of different weather stations around the world since I think like 1920 or something insane like that, a long time back. And it's basically data per weather station per day that weather station has been operating, and it's things like temperatures and information on storms, tornadoes, things like that. And all this data is there. Right now, we just have the station IDs that are shown there, but we're actually we've been working with that data and expanding that to kind of pre-join the longitude and latitude of those station IDs. So we're going to show you that here today. The data set you can't quite query yet, but we'll get that out to you soon as a public data set, or ping us on Google Plus if you're interested in that information. But we're going to show you two types of queries. And the first type of query is a simple bounding box. So you drew a box around San Francisco, and you want to figure out, what are the min temperatures, what are the average temperatures, within that bounding box. This is a quite simple inequality query. Just using the longitude and latitude and finding things within that box. And we'll show you how we do that here. And let me pull up that query. It's right here.
So essentially, you're just looking at to find coordinates that lie between the edges of the latitude-longitude boundary. And
exactly. It's quite simple here. And we're getting the average temperature and the max temperature, and we're using the group by and order functionalities to basically figure out the max and average temperature by month. And you see these data points start in 1948 for this particular set of weather stations. And the temperature, we see January at 55 max. Actually, we look at the average here. January at 50, February at 48, March at 49, and then it climbs back up. There's only small degrees of differences in the San Francisco Bay Area because it's a fairly temperate climate here. You should all come out here. We love it. But if we look at another area, we might find a little bit differences. And let's actually do that. But we're going to look at another area using a different technique. So we're going to actually look at the Denver, Colorado area doing a radius query. Now, this is a radius query of finding all the weather stations that are within a certain distance from Denver. I've hard-coded Denver in the query that you're about to see, the longitude and latitude, but you could actually get Denver from a map like this and do live interactive queries on the map. And we'll show you the fully polished demo and maybe release it as sample code sometime soon. But we want to find all the points that are within that radius. It's not the easiest query to do, especially in a highly accurate way. because of kind of the shape of the Earth. The Earth is generally a sphere, but the longitude and latitude converge as you get near the poles. And I don't think the Earth is actually a perfect sphere either. So there is a mathematical function that we'll show here, which is basically finding the distance between 2 points on a sphere. And so it's approximating.
Yeah, for a relatively small distance, it's pretty accurate.
Yeah. So let's show you that here. And
this is a great query because it uses some of the mathematical and trigonometric functions that are available in BigQuery, like sines, cosines. We have pi and average, and we're putting them all together in one query.
All right, so let's run that here, and we're doing a lot of different mathematical calculations on this large data set, and we're actually finding here around the Denver, Colorado area. The temperature is, actually it didn't group by months in this one, but the temperature here we're finding at distances from the different points within the Colorado, the different weather stations essentially.
This is interesting. You pull out microclimates from this type of information and kind of get the average around the different altitudes as well.
Yeah, exactly. So there's 38 points here that are within a distance of 100 miles. And actually, I am looking at a particular month here. I'm looking at August.
Yep.
So these are just the average temperatures in August.
I wonder if you change this to January or something, if it would be.
Yeah, let's go for February. I like February. So we have 71 degrees in each of these weather stations in August. And if we change over to February, we could see here that these weather stations are collecting over many, many years an average of 31,
so much
34,
colder.
Much colder, much less temperate climate. So I think that basically wraps it up in terms of the different types of queries that we wanted to show you here today. Definitely let us know what you guys end up doing with BigQuery. Let us know what types of queries that you have. Reach out to us on Stack Overflow if you have particular types of problems that you're trying to solve, and you can kind of formulate them as questions to other developers in the community. And if you just want to share with us a really interesting query that you found, share that out to us on Google+. You can look at the beginning of the video to see our Google+ profiles. We'd love to see what you're doing with BigQuery. And let us know. Thanks very much. And if you want to see a full guide of the different query syntax that's available in BigQuery, look on the BigQuery documentation, and there's a page there that just describes all the different query syntax.
We've heard feedback from you that you'd like to see some of the queries we demonstrated today in sort of a cookbook form, so we're working on that, and we'll put that on that page as well.
Yeah, exactly. I think we have to really crunch that in soon, because we really want to get that out there and show you the full cookbook of different types of queries. Also, just let us know what you're looking for. If there's types of queries that you can perform in other database environments that you really want to have in BigQuery, let us know. We'll take a look at it. The architecture of BigQuery, as you saw, is a little bit different. So, it may be more or less difficult to do it at the scale that BigQuery operates at, which is huge. But we'll definitely take a look, and we'd love to get your feedback. So, thank you very much. I'm Michael. I'm Michael. No, this is Michael. I'm Ryan. See, we're sitting in the wrong chairs today. But I'm Ryan.
I'm Michael.
And this is the Ryan and Michael show, or the Michael and Ryan show, however you want to refer to it. And thanks for coming, and we'll see you again soon.
See you next time.